Another common type of composition is to have the outside function be just the simple exponential function e to the x, and then the inside function is some other function. Like in this case, the inside function is 3x. You can see here that h is f composed g of x, right? F of g of x. So according to the chain rule, we're going to find the derivative of the outside, which the derivative of e to the x is e to the x, but we're going to have to find the derivative of the outside and evaluate it at the inside. So we're going to have to plug in 3x. To the derivative is the function that whatever you give it, it makes it the exponent on e, so we have e to the 3x. And let's see, then the derivative of the inside function in this case is 3, so h prime of x is going to be the derivative of the outside evaluated at the inside times the derivative of the inside, or 3e to the 3x. Here's another example where we have a function and the outside function is e to the x. So the outside function is e to the x. In this case, the inside function is tangent of x. So then the derivative of the inside, let's see, the derivative of the tangent is the secant squared, and the derivative of the outside function is e to the x. And the derivative of the outside evaluated at the inside means take the derivative and plug in the tangent of x. We can see in this case, since f prime is e to the x, if you give it tangent, you're going to get e to the tangent x. So h prime in this case is going to be the derivative of the outside evaluated at the inside, that's e to the tangent x, times the derivative of the inside, which is secant squared x. Now, just for safety's sake, I don't want someone to come along and see my sloppy handwriting and think that the secant squared and the tangent are up in that exponent. I'll just, since I can multiply in any order, I'll turn it around. And this may make it a little bit safer. So it's copying wise to put the secant squared out front. That's just kind of a personal choice, though. You can see that in these two cases, it doesn't really matter what the inside function is. We have here h of x is e to some function. Then the outside function is e to the x, and the inside function is g of x. So the derivative of the outside is e to the x, because the derivative of e to the x is e to the x. And the derivative of the outside evaluated at the inside would just be e to the inside function. So if we put that all together, h prime of x is going to be the derivative of the outside evaluated at the inside times the derivative of the inside. But the derivative of the outside evaluated at the inside is going to be what you originally had, e to the gx times g prime of x. So this is just a special case where the outside function is the exponential function. Maybe for safety's sake I should turn around and write g prime of x times e to the g of x. It's up to you. Alright, that's the generalized power rule. I'd like to call your attention to one specific special case of this special case, which is when you have e to some linear function, like e to the kx. Then the outside function is e to the x, and the derivative of the inside function, so the inside function is linear, so the derivative is just the coefficient of x. So if you apply this rule in that case where the function is some constant times x, then the derivative of e to the kx is going to be e to the kx, right, times k, or if I turn it around, ke to the kx. So these two rules ought to become pretty automatic for you, so make sure that you memorize them. Also ought to memorize that generalized power rule as well, because it just comes up so often, and derivatives are just sort of the air we breathe in calculus, so you want to have these derivatives memorized. So if somebody asks you, hey, what's the derivative of e to the 17x? You just say, oh, it's 17e to the 17x. Or if someone says, what's the derivative of e to the negative x? You say, well, in this case, k is negative 1, right? So the derivative should be k e to the kx. So negative e to the negative x. Or if someone says, what's the derivative of e to the sine of x? You just say, oh, it's cosine x, right? E to the sine of x. It's just the generalized exponential rule. Here's another example. We've got some exponential stuff going on here, and then our outside function is is to the fifth power. So our outside function is the function that takes things to the fifth power. Our inside function is e to the x plus e to the minus x. So if we want to find the derivative of the inside, well, the derivative of e to the x is e to the x, and the derivative of e to the negative x is negative e to the negative x. So we have e to the x minus e to the minus x. Okay, so the outside function is a power, so the power comes down, we get the inside function. So 1 power less, 1 less than 5 is 4, and then times the derivative of the inside function, which we knew would be e to the x minus e to the minus x. Here's one more example. In this case, we've got a really big chain going on here. So we have e to some function. So if we want to find the derivative of h with respect to x, we could apply the generalized exponential rule, right? Just this special case of the chain rule. We know we're going to get e to that function times the derivative with respect to x of the inside function. Now that inside function is sine squared, so that means the sine of 3x minus 5 all squared. Now this is a case for the generalized power rule, right? When you have a function to a power, the power comes down, you get the function to 1 power less times the derivative of what's inside. So to take that second derivative, or the derivative of this inside function, the 2 is going to come down. We're going to get the sine of 3x minus 5, and then we'll multiply that by the derivative of what's inside, which is the sine of 3x minus 5. Now finally, to take the derivative of this, we have this linear function, 3x minus 5, inside the sine function. So applying the chain rule to find that derivative of this innermost piece, the derivative of the outside is cosine. Evaluated of the inside gives you 3x minus 5, and then you have to multiply by the derivative of the inside. The derivative of 3x minus 5 is 3. So we've actually had to use the chain rule 3 times. So we had e to some function, so we had a function inside a function. But then to find this derivative, since that was a function raised to a power, we had to use the chain rule, or actually a special case, the generalized power rule. The power came down, we got the function to 1 power less times the derivative of what's inside. And then we had another chain, right? So we took to get the derivative of that, we took the derivative of the outside, plugged in the inside, and then multiplied by the derivative of 3x minus 5, which is 3. Now I could, a lot of times I'll just put the stuff that's multiplied out in front. I've got 2 times 3 would be 6. There's a sine of 3x minus 5 and a cosine of 3x minus 5, and that's multiplying e to the sine squared 3x minus 5. So I have it done. So keep in mind, you might have to use the chain rule multiple times in order to finish the problem. Just think about it step by step. So we applied the chain rule, we had to take the derivative of that. Then to take the derivative of that, we had to apply the chain rule. And as part of the chain rule, we had to take the derivative of sine of 3x minus 5. So we had a function inside a function, so we applied the chain rule again. So watch out for that. Also watch for chain rule in combination with products or sums or quotients, so you'll have to use those rules as well to get the job done.